All right, so chapter 3. We're going to start chapter 3. Obviously, you can already tell it's a pretty long chapter. I'm going to try my best to kind of keep these videos to a minimum, but unfortunately, section 3.1 is, the introduction. So we're going to do almost all of it, except for the last problem. We'll do that together in class. So, derivative of a function. The study of the rates of change of a function is called differential calculus, which means finding the derivative. Our study of rates of change has already given us our first look at the derivative. So you guys have already seen the definition of a derivative. So in this section, we're understanding what derivatives are and what they represent in real-world situations. And then we're going to interpret graphs of a function and the graph of its derivative. So we've already seen how to calculate derivatives using the basic limit definition. So let's kind of review that now. Okay, so if you remember, the limit as h approaches 0 of f of x plus h minus f of x, all of that is divided by h. That is the slope of the tangent line, aka also the instantaneous rate. And now, actually, based on this, it is also, I'll write it right here, it is also going to be known as the derivative of x. So a quick example in your notes, okay, in the one that you printed out, it says a problem that dealt with calculating the instantaneous rate of change of the surface area, s equals 6x squared of a cube with the edge length a at x equals a. So right now what we're going to do is we're going to use the instantaneous rate. So the limit as h approaches 0 of f of, and what is our x in this case? Our x is a. F of a plus h minus f of a. So all of that is over h. And then remember, you take this, you plug it in to x for that formula. So we get 6 times a plus h squared, and then minus, this whole thing is put in parentheses, 6 times a squared. All of that is over h. And I don't have to redo this whole entire thing, but you guys know how this goes. You FOIL first. So you have your a squared plus 2ah plus h squared minus 6a squared over h equals, distribute the 6, so 6a squared plus 12ah plus 6h squared minus 6a squared, and you notice that these cancel out and you're left with 12ah plus 6h squared over h. Now I'm going through this really quickly. You guys can probably go through it even quicker. And then you notice that the h's cancel out all except that one, and you're left with 12a plus 6h. And then as the limit of h approaches 0, then we know this guy right here turns into a 0, so all we're left with is 12a. And guess what? 12a is the derivative of 6x squared at that point. So, what is the definition of the derivative? Okay, the notes, unfortunately, that I printed out are a little different. So, what is the definition of the derivative? The derivative of the function f with respect to the variable x, so we're always focusing on x, is the function f prime, okay, we'll look at those notations in a minute, whose value at x is f prime of x equals the limit as h approaches 0 and are instantaneous, provided that the limit exists. In section 3.2, we'll look at when it doesn't. Now, graphically, we remember that the tangent line is at a point. It's at one point, correct? And basically, our derivative is going to be the slope at that point, the slope of the curve at that point. So if I was to ask you, what is the slope of the curve at this point? It's 0, correct? What is the slope of the point right here? It's negative. What is the slope here? It's 0, right? And when I'm asking what is the slope, I'm basically asking the derivative. Okay, what is the slope here? It's negative. The slope here is positive, and we'll look more into that in just a minute. All right, so let's go back to this. So this is called the four-step method. The four-step method, which actually you guys kind of already do in one step already, okay? First, we find f of x plus h, so we plug this in. And then we subtract f of x from f of x plus h. And then we divide h. And then the last thing we do is find the limit as h approaches 0 of the whole entire function. So this is called the four-step method. And you guys are already doing this, so this is nothing new. Okay, you can pause the video if you want to write down the four-step method. Now, notations and pronunciations in this chapter. So there are many ways to write a derivative. So there are many ways to write the derivative of y equals f of x. So the derivative of that function. One way is f prime of x. So that's exactly what we say. It's f prime of x. Okay? And you're basically, for all of these, you're going to be saying the same thing. It's the derivative of f, of the function f, with respect to x. Okay, and this statement is going to go to all of these. So another way, instead of f of x, we know that we can write down y. So we can say y prime. So y prime, which also means the derivative of y with respect to x. Okay, another notation is dy over dx. So this is not die over dx, okay? It's dy. You literally say it dy over dx. Okay, and this is the derivative of y because we have y. So it's the derivative of y with respect to x. And of course, just like y, we can also put down df dx. And this is the same thing. It's the derivative of f with respect to x. And then the last way is d over dx of f of x. So it's d over dx of f of x. And this one we say it's the derivative of f of x. It actually still means kind of the same thing. You're just finding the derivative of f of x. This one, you're finding the derivative of the function f with respect to x. You're finding the derivative of y. You're finding the derivative of y. You're finding the derivative of f of x. Okay? So, this is nothing new. We're going to use the definition of derivatives. And what is the definition of derivative? It's the thing that you guys already know, the instantaneous rate. We're going to use the definition of derivative to actually find this derivative. So, f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. So remember, you first plug that in. So it's the square root of x plus h minus, plug this in, square root x. And then all of that gets divided by h. Now this is something that you have to keep in mind, because looking at this you cannot simplify that any further. But if you remember, if you have two radicals, how can we get rid of them? What can we try to do and see if it works? Is we can multiply by the conjugate. So we multiply by x plus h plus square root of x over square root of x plus h plus square root of x. All right, so I'm going to bring this over here. I'm going to keep going. So now the limit as h approaches 0, you FOIL this out, and what do you notice happens when you square root of x plus h? The square root is gone, so you're left with just x plus h. And then the outers and the inners do what? So these outers and inners cancel each other out, so I don't need to worry about them. And then the last term, which is negative square root of x and positive square root of x, give us minus x, because square root of x squared is just x, right? Recall, square root of x squared, what does that square do? Just cancels out the square root and you're left with x. And all of that is over, not just h anymore. So now we have h times this guy. So h times the square root of x plus h plus the square root of x. Okay. And now we simplify the top. So x plus h minus x, what happens to the x's? They cancel out, so you're left with just h on top, and on the bottom we have h times square root of x plus h plus square root of x. What happens to these h's? They turn into a 1, right? They don't cancel out because we still have a denominator. So this is 1 over the square root of x plus h plus the square root of x. And now we can apply the limit, because this is as far as I can go. There's no point in multiplying by the conjugate of this, because I'm going to get back to where I was. And remember, the only reason we did this is because right now if I plugged in 0 in for h, what happens to my whole problem? It's undefined. So I needed to do something to maybe get rid of that, and that's what this helped me do. So now if I plug in 0 in for h, what am I left with? 1 over the square root of x plus the square root of x, which is the same thing as 1 over 2 square root of x. And guess what? The derivative of that function is, in fact, 1 over 2 square root of x. Now, they didn't give us a point. If they would have given us a point, I would have plugged that in for the x. But right now, they just said find the derivative using the definition of derivatives. All right, so at this point, you can kind of stop the video and try to do this problem on your own and see if you can get it done, and then start it up again and check your answer. But this is asking, find the derivative of y with respect to x. And again, we're using the definition of derivatives here, so we're using what we know. So dy dx is the same thing as saying the limit of h approaches 0 of f of x plus h minus f of x over h. So we're going to plug in x plus h in. So 3 times x plus h minus 12 minus, now we're going to plug in x, which is just 3x minus 12. All of that is over h. So we simplify. So this is 3x plus 3h minus 12 minus 3x plus 12, right? Because this negative needs to get distributed to both of these. So plus 12. And right now I noticed that my 3x's are gone and my 12's are gone. And what I'm left with is just 3h over h. And what happens to these h's? They turn into a 1, and I'm left with 3. And that's it. So then the derivative of y with respect to x is actually 3. Now remember, this notation is the same thing as this notation. Now we're not going to use f here because they just didn't give us f of x, they gave us y. Alright, so still nothing new, right? Now here's where it gets a little fun. So relationships between the graphs of f and its derivative. So we can get a good idea of what the graph of a function derivative looks like by estimating the slopes of the various points along the graph. So basically, if this right here, consider the graph f and the of f below. So this right here is my f of x, and this right here is its derivative. And let's pay attention to what's happening. So if I was to estimate the slopes, okay? So right now, if I look at this graph, what is the slope at this point right here? If I was to estimate it, draw my tangent line, right? And it's going to be kind of hard, but just bear with me. So if I draw my tangent line, my slope at this point right here is going to be about, and actually I don't know why I curved in like this, because really it should go up straight. Rise over run. So what's the slope at this point? So the slope at f of -1 the slope is. Rise is, let's say it's 1, 2, 3, 4, 5, 6, 7. Okay? And then run is 1. So what's my slope? 7 over 1. So guess what? At -1, where do you think my graph is going to be? At 7. And it's about there. 1, 2, 3, 4, 5, 6, 7. I can honestly say that it's approximately over there. Okay, if this graph was to keep going. Now at 0, if I was to also try to find the slope here, if I had a perfect ruler to figure out the slope, I would say that at 0 the slope is about 1. There's a rise of 1 and a run of 1. So guess what? At 0, my graph, my derivative, is going to be at 1. Okay? Now you notice that at 2, right here, what is my slope? Okay? So my slope at 2 is 0. So at 2, approximately, okay, right? We're a little bit off. Approximately, it's 0. So basically, I can identify a few things from this graph. Okay? So I can say, right, 3 things that we can tell about the behavior. When the slope was positive, it means if the slope is positive, that means the function is what? Is increasing. Right? So if the slope is positive, it means the function is increasing. And remember, the derivative is the slope. The derivative is the slope at that point. So if the slope is positive right here, that means the graph is going up. If the slope is negative, that means the graph is going down. And if the slope is 0, that means we probably have a 0 or a local max or a local min, depending on what's happening at that graph. But we'll talk about that in just a sec. So one thing, a positive derivative, we're going to call that a slope, means that f of x, the actual function, is increasing. A negative derivative means f of x is decreasing. And then 3, a 0 derivative means that the function has some special behavior at that point. It may be a local max, local min, or a 0. All right, so let's look at that. So here's the derivative. So right here, the derivative is what? The derivative is, what is the slope? All the way here. It's negative. So if the derivative is negative, what does it say? I'm sorry. What is the derivative all the way up until this point right here? The derivative is positive. So up until that point up until x is 0, my function should be increasing, which it is. Okay? So then after that, what is the derivative? After this point right here, right after 0. So like again, right after 0. My derivative becomes negative. I'm in the negatives here. My y becomes negative. So what that means is that my graph starts decreasing. And then here, what is the derivative? The derivative is, where am I? I'm decreasing all the way. See, this is just a bad graph. Let's look at the next one. The next one kind of explains it better because this graph compared to this graph is just a bigger picture. So it's harder to see where the 1 is, where the 2 is. Okay? So let's do, this is our last example for the notes. I know these notes are going to be long, so just bear with me. Okay? All right, graphing f from its derivative. So this right here is the derivative. We want to sketch the actual graph. And we have to follow a few things. First off, sketch the graph of the function that has the following properties. F of 0 is 0. Okay? So I know that f of 0, because this is going to be my f of x, at f of 0 is 0. So I know that. Now, based on this graph, these should be open circles right here. Based on this graph, when x is less than 1, what is the slope? So when x is, greater than 1, what is the slope? The slope is 2. Okay? Or I should say, what is y? What is the derivative? Okay? So it is 2. It's at 2. So what is y? It's 2. So guess what? When x is greater than 1, all right, my slope on this side, so here is the point of discontinuity, but my slope on this side is going to be 2. And then when x is less than 1, what is my y? My y all the way through, okay, is -1. So that means what this translates into, to the actual function, is when x is less than 1, my slope is going to be -1. Does that make sense? I hope it makes sense. So on this side of -1, starting here, let's do a slope of -1, which means I'm going to fall 1, run 1. Now, on this side, it's going to be different, so I'm going to keep going. So how do I make a slope of -1 from here? I'm going to go up 1, left 1. Up 1, left 1. And there's my graph. And I know it's going to be consistently -1. So on this side of -1, my slope is negative. On this side of 1, my slope is -1. But when x is greater than 1, what's my slope? My slope here is 2. Okay? So starting at this point, now what is my slope? Is going to be 2. So I'm going to rise 2, run 1. I'm going to rise 2, run 1. And there's my, and because I know it's constant forever, I can kind of make my little graph. Okay? And the graph of the derivatives is f of shown, and then is it continuous on all of x? Yes, it is. So you guys see the difference between the two? So basically, if I wanted to go back here, I would basically identify the slope right here. This is negative slope, negative slope, negative slope. And what is the slope exactly? It's -1. So at every point in x on this side, so at -3, it's going to be -1. At -2, it's also going to be -1. Okay? At -1, it's also going to be -1. At 0, it's also -1. Up until we get to 1, and then it changes. And when it changes, it jumps. So you have to be able to make these two connections. All right, I know the videos are long, but you guys will do this problem tomorrow or maybe even Friday in class together. We probably won't even get to it tomorrow. All right, good luck.